In this video, we are going to learn about one of the very important topics in calculus called the related rate problems. So what are the related rate problems? Problems where the rate of change of one variable depends on the rate of change of another variable. So the rate of change of one variable depends on the rate of change of another variable. Rate of change of another variable. So there are a lot of questions like that in mathematics. So let's look at a few examples. For example, blowing a balloon. So if you blow a balloon, what happened? And you can see, so you put the air into a balloon, and then when you put the air into a balloon, so what will happen is gonna increase the volume. So it's gonna increase the volume. So when you increase the volume, and we assume that there is like a spherical shape, so what will happen is gonna change the radius. So you can see when you change the volume, it's going to increase the radius. So that means there are a lot of things happening here. So that means the volume and the radius are related to each other. So that's the kind of problem that we're going to study in this one. So as the next one, think of filling a tank. So let's say, so there's a tank, and then so let's say like a conical tank. And then what we can do, we're going to pour water into it. So we're going to pour water. So what will happen, then you can see the water level increases, and then so you can see this radius of the surface actually change. It's not like it's the same. It's like when it is at the bottom, it's like a small radius, but when it go higher and higher, you can see the radius changes. So that means the so rate of change of the water, the volume, and the rate of change of the radius are related to each other. So those are the kind of problems that we can look at under that topic. And then as the next one, so we have what we call the chasing a car problem, or sometimes we also look at like other objects like the planes and stuff like that. So what's going to happen in this situation is like you can see. So let's say there are two like converging cars. So there's like a car going to the north, and there's a car going to the east. And then what happen is, let's say it's passed through a junction. So what happen is you can see the distance between these two changes with respect to time. And then so we can ask a lot of bunch of questions like in a situation like that. So those are and then also the things can be much difficult, like if they are not like perpendicular. Let's say like there's an angle here, so then the things would be much more difficult in such a situation. So we might you need the cosine rule for a problem like that, or sine rule for a problem like that. Okay, so let's look at the next type. So as the next one, we can look at a problem like a sliding ladder problem. So let's say so there's a ladder against to a wall, and then what happen is, so there's a ladder. What happen is maybe like one side slips away from the wall. So when one side slips away from the wall, and you can see that the top goes down. So and then they are related to each other. How fast one change, and then also you can see that those rates are not the same. So this is the kind of problem that we can study from sliding ladder problems. So let's look at the next type. So the next one is like motion of a particle. Like let's say like a particle follow a special path, and then what will happen is those x and y coordinate changes depending on the path. So for example, one nice example would be, let's say a particle change on a circle. So so it's something move on a circle, and then you can see those two quantities, the x and y variables, are related to each other in this one. So that means if you know the projections and the speed of those projections, and you can relate them using the equations. So this is like a circle. So those are the kind of problems that we can look under motion of a particle situation. And then also, like, I have a really nice animation created for this one, and then you can see that when we do the problem. Okay, so the next one may be so we can have like quantities related by an equation. This is like a very common problem. So you can find these kind of problems in like any STEM major, or like a lot of situations like that. So for example, let's say we have a problem like let's say x times z plus y squared plus z to the cube equal 7 or something like that. So this there's equation, and you can see that those quantities are related to each other. And then if you know derivatives of one variable, and then you can find derivatives of other variables just simply using chain rule and the implicit differentiation. Those are the kind of problems we can study in this one. So we can study actually 7 different examples. So let's go one by one. So the main tools to study related rate problems are the chain rule and the implicit differentiation. So, if you are not familiar with the chain rule and implicit differentiation, please make sure that you study those two first. Otherwise, these problems will be a little difficult. So, and you can find the link in the description for those two topics. So, and the idea is you first find an equation that relates the quantity. So that's the first step. So you're going to find an equation. So you write an equation that combine those variables. So we introduce variables, and we're gonna find equation that combine the those two those quantities. So the second step is we're gonna use chain rule. So use the chain rule and the implicit differentiation to find the related derivatives. So that's why we call related problems, related rate problems, because they're related derivatives. So these kind of problems have like a 6 main steps. Uh, so these are the 6 steps that we try to use for a problem like that. So make sure you follow those steps, and then you can get the answer very quickly. So the first step is draw a picture. So you're going to draw a picture describing the situation. That's really helpful to do a problem like this one. So you draw the picture, and then you introduce variables. So you draw a picture, and then what we do, we introduce variables. That's like a very important step. We introduce variables, and then using those variables, you can identify the constants. There are several constants given, so you can identify them. Normally, like we use t for time, and then x, y, z like variables like that for distances. So they're like the common practice. And then major step is we can write down all the given information using the new variables. So we can use new variables to write the given information. Use the new variables. And then you can identify what you're going to find. Because if you don't know what you find, I mean, there's no way like you can do this problem. So you can identify what you are going to find in this problem. That's the next step. And then the most important step is after you know what you're going to find, you're going to write an equation. You can write an equation that relates the variables. You write an equation that relates the variables. It will be very clear when we do the problems. And then we differentiate the equation using the implicit differentiation chain rule. That's the main topic, main tool here. And then we're going to find the unknown. We use the known information to find the unknown information. So those are the 6 major steps in a related rate problems. So now let's go one by one. So as the first example, we have the blowing a balloon problems. It's like a very common problem that you're going to encounter in courses like this. So let's read the question and try to understand what's really going on here. So what it says that the air is being pumped into a spherical balloon. It's very important information. It's like a shape of a sphere, spherical balloon, like a ball. So that its volume increases at a rate of 100 cubic centimeters per second. So each second its volume increases 100 cubic centimeters. And then the first question is asking, and you can see that when you blow the balloon, its radius increases. So they are actually asking the same questions, asking how fast is the radius increases. Radius increases when the diameter is 50 centimeters. When the diameter is, these numbers are really like easy numbers, that's why we pick numbers like that. So how fast the radius of the balloon increases when the diameter is 50 centimeters. Why we need the diameter? And you can see that the rate changes depending on the diameter. And like like when you blow a balloon, you can see it changes at the beginning. It changes really fast, and then later you can see you cannot even see like even though you blow the balloon, you don't even see much changes. So that means so depending on the diameter, it change the rate of the change of the radius. And the next one is asking what will happen to the rate of change of the radius when the balloon gets bigger. So that's exactly what it's asking. It's asking what happens when the balloon gets larger and larger, what will happen to the rate of change of the radius. So let's try to see the problem and how we can solve this problem. So one interesting step would be to draw the situation. So we're gonna like draw a picture to explain the situation, because that can definitely help you to understand what's going on. So let's draw that. So we have a spherical balloon, and then what we do, we pump air into it. So when you pump air into it, and you can see it increases, the volume increases. So it gets larger and larger. So it gets larger. So, and then you can see it radius changes. So we're gonna mark the radius here. So those are the important information that we have for this one. So what we can do, so that's the first one. So we draw a picture for the situation, and then we're gonna pick variables. So there are like common variables that we can pick. So one common variable would be, we're gonna say V. We're gonna pick V for the volume, and then we're gonna pick R for the radius. So we can write it down. So let's write it. So let's say let V be the volume. Let V be the volume uh, when, you can say, when the radius, when the radius, when the radius is R. So that's the first step. So you're gonna name the variable. What variable you're gonna pick for this situation, and it's very clear that those are two variables that we're gonna pick. So we pick V for the volume and the R for the radius. Okay. So, and then what we can do is we can actually mark those things that we already know, and you can see that we are given that the volume increases at a rate of 100 centimeters per second. So that means we are given dV by dt, because that is the rate of change of the volume. It says that it is 100 centimeters per second. 100 centimeters per second. So we write the given information using the variable that we pick. So that's the next step. And also we can write a relation. We can write a relation that combine V and R. And we know this formula from high school. What is the relation between a volume of a sphere? So, and then you can see in this problem, actually what we're trying to do is we need to find, so you can say need to find dr over dt when the radius, so you can see the diameter is 20, diameter is 50. So diameter is 50, radius is half of that, so that means it is 25 centimeters. So that's the radius. So what we need to do is we need to find dr over dt when r equal 25 centimeters. So what we now what we now do is, like, we're going to find a relation that combine the V and T. So as I said earlier, we can write the formula for the volume. So we know that the volume of a sphere, volume of a sphere is given by V equal 4/3 pi r cube. So if you don't know those formulas, there are like formulas for those common geometric figures, and then you can find a link in the description to find all of those common things that you need to know in a calculus class. So yeah, you can find that in the description. Okay, so this is the formula we're going to use, and then you can see that in this case there are two variables. One is the V, so it's a volume. Uh, so this is a variable because you can see it changes with time, so it's a variable. We will also have another variable here, radius. This is also a variable, and you can see they are all change with respect to time. When time changes, those two are changes. So that means we can find the rate of change, because since they change, we can find the rate of change. So yeah, so you can see that. So you're going to change with respect to time, change with respect to a time. Time we normally use as a t. So those are the common things that we do. Okay, so now what we can do is, so we know the relation, so that's the relation we're going to use that combine the v and r. Now we take the derivative with respect to time. So that's why we need to use the chain rule, because you can see the time is not appear here. So that means we had to use the chain rule for a problem like this. So let's use a chain rule to find the derivative. So we are going to differentiate both sides with respect to time. So differentiate both sides with respect to time. So time we normally use the t variable. So that means, so what we have is we have v equal 4/3 pi r cube. So what we can do, we get the derivative with respect to time. So and then you can see that time is not a variable here. So we can take the derivative with respect to time of v on this side. On the other side, we take the derivative again with respect to time of the quantity given, so which is 4/3 pi r cube. So this is a step we have to use the chain rule, and you can see on the right side what we can write. We can write this one as dr over dt first of the quantity, because that's what we have, r3, and then we multiply by dr over dt. So there is a chain rule step. That's a chain rule step, and you can see clearly we have the dr term here, and then we have dr term here. Again, if you are not familiar with the how to take the how to use chain rule, and please look at the video given in the description. Okay, now we can actually simply take the derivative, and you can see if you take the derivative with respect to r of the first term, and you can see that you're going to get 4/3 pi, and then if you take derivative with respect to r, you get 3r squared. So that's what happened from the first term. That's what you get from the first term, and then times dr over dt, and you can see this simplifies. So you're gonna get 4 pi r squared dr over dt. And if you are familiar with the geometry, and you can see that 4 pi r squared is a surface area of a sphere. So it's kind of nicely appear here in this equation. Okay. So now what we are going to do is, so that is the major equation. So what we're going to do is now um, you're going to see this equation relates dv and dv over dt and dr over dt. So this is the related rate equation. So you can see though this equation relates the two variables that we are looking for. Now what we're going to do, we're going to use the given information and plug in it here and find the find the unknown using the known. And you can see we are given dv over dt, so we know this one, and we also know the r. So only thing that we need to find is dr over dt. So this is very easy. So we're going to plug in here and find that information. And so you can see that, so you can say this equation, so it's clearly this relates dv over dt and dr over dt. Okay, so that's why we call these are related rate problems. They relate the two variables. Okay, so let's use the given information to find the unknown. We need to find the dr over dt when r equal 25 centimeters and dv over dt equal 100 cubic centimeters per second. So what we're going to do is, first we can solve for dr over dt. So we can write the same equation like this. So we can say dr over dt equal, if you divide both sides by 4 pi r squared, so you're going to get a 1 over 4 pi r squared dv over dt. So it's a good idea to write it like that. And then what we can do, we're going to plug in the values. So we have a 1 over 4 pi, and you can see r is 25 centimeters, so it's a 25 centimeters squared times dv over dt. So dv over dt is 100 cubic centimeters per second. And then you can see centimeter squared cancel with the centimeter squared. So you can cancel this with this, and you get only 1. And then also 4 times 25, 125 is 100, so that means you're going to cancel out. So 1 of the 25 get cancelled out, so that means you end up getting 1 over. So there's a So you have 25 pi. You have 1 centimeters and a second. So, and it says that, so the radius changes at that time 1 over 25 pi centimeters per second. And if you use a calculator, the approximate value would be 0.013 centimeters per second. Okay, so that's the answer for this problem. And then what we normally do is we can write this in word. So you can see we write this one as the radius of the balloon increases at the rate of, so we can write it. So the radius of the balloon is the balloon increases at a rate of the rate of uh, you can write the exact value if you want, or you can write the approximate value 0.013 centimeters per second when the radius is 25 centimeters. It depends on that. Okay, so that's how you solve the problem. So let's look at the second part. In the second part, it's asking what will happen to the rate of change of the radius when the balloon gets bigger. So this is like a theoretical question, and you can see, you can look at the same equation. Remember we had dr over dt, which is equals to 1 over 4 pi r squared dv over dt. And this says that because you can see that this is a constant right now. These are also constants. So if you remove them, if you ignore them, you can write this one as dr over dt is proportional to 1 over r squared. So this is what we call inverse squared law. Inverse squared law. It's normally called inverse squared law. Inverse squared law. This is like a very common situation in sciences. So what it says that when r gets bigger, and you can see because you see the denominator, when r gets bigger, the dr over dt gets smaller. So this is exactly what we see in the nature. When we blow a balloon, you can actually see that at the beginning it's grow really fast, but later it's going to slow down. It's going to slow down. So so if you draw this with respect to time, um, and then so you can see it's like a start at the beginning it's like large, and then it's going to slow down. Okay, so yeah, actually I didn't know, right, it actually goes to infinity if you look at the real situation, but like that's not practical, so we can't ignore that, and we start with a certain value. So that's why we write it like that. Otherwise this has to go to infinity. It's like how to handle the practical situation. Okay, so and then we can write this in words. So we can see that when, so let's write it. When r gets bigger, you can see when r gets bigger, uh, the rate of change, the rate of change, the rate of change uh, of the radius, this is dr over dt, rate of change of the radius gets small. So that means actually that means we don't see much changes. That means we do not see much changes later. So this is like a very common, so we have seen this one. Okay, so let's look at the next problem. As the next problem, we have a sliding ladder problem. These are very common problems in mathematics, and we have really nice geometry here. So and then in practice what they normally do is they put like something at the bottom just to prevent sliding. But as a mathematical problem, let's see what we can do here. So what it says that a 13-foot ladder leans against a wall, vertical wall. If the foot of the ladder slides away from the wall at the rate of 2 feet per second, how fast is the top of the ladder slide down when the bottom is 5 feet from the wall. So it's very clear what happened. So there's a ladder, lean against a wall, and then what happened? You can slide down, slide the bottom, slip away from the wall, and then it's given like what's the rate? So 2 feet per second slips away from the wall, and then what happened to the top? And you can see clearly top goes down. Also from mathematics, it's very clear a top has to go down. So let's look at the mathematics part right now. So we can draw a nice picture for this one. So we have this. So we have the two walls and the ladder. So the ladder, and then what we can do is we use variables here. So what we can do is we can take this distance as x. So this is x, and then this one as y. So the height is y, and the distance is x. And you can see, so it's gonna slide down this way. So that is the rate of change of x. So that means this is a dx over dt. So this is a dx over dt, which says that it is 2. It is positive and it's 2. And the ladder, which is 13 feet. So this is a 13 feet ladder. 13. And also see whether the variables match, whether everything is given in feet. Okay, so and then we also assume that this is 90 degree, otherwise things would be very difficult. And then so you can see uh, and then we can write a relation. So let's assume the variable. So what we're gonna do is we're gonna write the variables now. So we're gonna say uh, actually in this case what we are looking for is dy over dt. So we are looking for dy over dt when x equals 5. So that's the situation. So let's name those variables. So we're gonna say so let x, it's very important for our problem also to name this. So let x be the distance be the distance and y be the height. So that's a starting point. So we can say x is the distance and y is the height. So now after we get that, and then what we can do is we can rewrite those information given here, and you can see right after you get the variable, so it's very clear. So we have dx over dt equal to feet per second when x equal 5 feet. If it is inches, things can be different. And then what we need to do is need to find a dy over dt at the same time. So that's our goal. So we're going to find dy over dt. So that means we need to find a relation that combine x and y. So it's very clear that from the Pythagorean identity, so by the Pythagorean identity, uh, identity, by the Pythagorean identity, we can write as x squared plus y squared equal, from the Pythagorean identity, 13 squared. 13 squared, which is 169. Okay, so we have a relation now. So there's a relation that combine x and that relates x and y. Now what we can do is, and you can see that both x and y changes with respect to time. So we can differentiate now. So using the chain rule, differentiating uh, with respect to time, with respect to t in this case. So we take the derivative with respect to t. So it's a derivative with respect to t of this side, which is x squared plus y squared, equal the derivative of the other side. So now we take the implicit differentiation of both sides. So let's look at how it works. So first we take the derivative with respect to x. and then multiply by dx over dt, that's a chain rule part, plus the second term, we take the derivative with respect to y and then multiply by dy over dt, and the other side you can see it's a constant, so derivative is 0. That's what you get. And then we can simplify this one. So you can see that it's a 2x dx over dt, or you can write x prime here. And then it's a 2y dy over dt is equal to 0. And then you can see if you divide both sides by 2, so we write the more simplified form just to make calculation easier. So we can write this one as x dx over dt plus y dy over dt. So that is the mathematical equation that combine the x and y. So these are normally called differential equations because these are derivatives here. So it's a differential equation that you're going to learn in a different course. So these are normally called differential equations. Differential equations. Okay. Now what we can do, we can use the known information to find the unknown, and then you can see that in this problem you have x and y. X and y. So that means we need to find the corresponding y for this problem. So let's do that. So again, by the Pythagorean identity. So by the Pythagorean identity again, um, so you can write this one as 5 squared plus y squared. So we're going to find the corresponding y. 5 squared plus y squared equal 13 squared. And this going to give you y squared equal 13 squared is 169. 5 squared is 25. And then we can subtract this, so you get 144. And when you take the square root, you get y equal 12, because you know that this is a positive quantity. So you don't get the negative value here. Okay, now what we can do, we're going to plug in all those values. So we know everything now. So you can see we know x, we know dx over dt. We also know y. Only thing that we don't know is dy over dt. So it's very easy. We use this equation to find the unknown value. So let's plug in this now. So again, the equation is x dx over dt plus y dy over dt equals 0. So that means, so then we can write the value. So we're gonna plug in with the units. So it is 5 feet, that's x value. Dx over dt is 2 feet per second, and y is 12 feet, and then dy over dt that we don't know, that's what we need to find. So we use a known to find the unknown, and then what we're going to do is we're going to simplify this and solve for dy over dt. So so this says that, this implies that dy over dt equals, so if you multiply, and then also you can see there's some way units gonna get cancelled out, so you can cancel the 2 feet, and then you only left it feet per second. Good. So what's the dy over dt is, and you can see it's clearly it's going to go to the other side. That means it's going to be negative 10 over 12, and then unit is feet per second. It's simply coming from here, and if you simplify, you're going to get this is negative 5 6. You need to write this in the more simplified form. That's we normally consider as the final answer. So that's the final answer. And what we normally do, we actually write this in word as a final line. So we write like this. So you can say thus, the top of the ladder is sliding down. Why we say sliding down? See the negative sign. So negative sign means dy over dt decreases with time. Decreases with time. So it's very clear. So mathematically, it actually comes from this this problem. It should be going down because there's a negative sign here. Okay, so is sliding down at a rate of, you can say at a rate of 5 over 6 feet per second. When you say sliding down, you don't have to say negative because it says sliding down. So it's very clear. Okay. Or if you say just a rate of change, if you just say the height changes, then you have to say just negative 5 over 6. But if you say sliding down, you just need to give the value. Okay. So let's look at the next problem. as the next problem, we have very interesting one. So what is this? These are what we normally call filling a tank problem. Filling a tank problem. So what is this? A water tank with the shape of a inverted, I mean upside down, inverted circular cone has a base radius of 3 meters and height of 6 meters. If the water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising. It's very clear water level has to rise because the water pumped in. When the water is 3 meters deep, the reason is you need that information because you can see it changes. Like it's like a blowing a balloon problem. So let's look at the geometry. For these problems, like we normally use several geometric figures, and then we try to find the volume of those ones. And those formulas actually you need to remember. And if you don't remember those things, and you can find a link in the description to remember those all those special formulas that we normally use in calculus classes. Okay, so let's look at the situation. So there's a water tank. And what happened here is it's gonna pump water in there. So it's gonna pump water. So what will happen is the water level rises. So the water level is gonna rise. So what we're trying to do is like so you can see. So we need some information here. So we're gonna mark a few things here. So this is like a little long problem. So we have this few information here. So we need to know what is the radius of this one, and so base radius is given, which is 3, and also we need to know what is the height of this small cone shape water. So it's like, so we have water here, so we know what is the volume of this one, and also it is given that this height is 6 meters. So that means there's a nice geometry here. So if you look at this special triangle here, so you can see, so we can use this special triangle for this problem. Yeah, so it will be very clear. Okay, so let's try to pick some variables here. So one of the variable that we need is the radius of the water cone, height of the water cone. That means this part, that's the height of the water cone, and also the volume of the water cone, this one. So those are the three variables we need this problem. You can see all three changes with time. So let's write that first. So we can see let R, H, and V be the radius, height, and the volume of the water cone at time t. At time t, because you can see it changes at time t. So it's very important at time t, respectively. So we don't write it here. And then what we can do is from high school geometry, and you may remember this formula. So then the volume of the cone is V equal 1/3. You can see all the cone shaped ones has a 1/3. Even the volume of a sphere. So pi r squared, that's the base area, times the height. So that's the formula. So this is like a formula you have to remember from this is something that you'll remember. Okay, so V equal 1/3 pi r squared h. And you can see there are three variables. So what we're trying to do is we're going to bring these two variables. Like because there are two variables here, we're going to make it one variable. So that means write the equation using only two variables. That's one of the steps that we're trying to do. Bring it to only two variables. So for that, what we can do, we can look at the geometry again. So so as before, so we have that special triangle here. That's a 3, and then we have this triangle, and then we can mark the given information. So so we have the radius of the water and the height of the water, and then these are all 90 degrees, so that means there are two similar triangles here, and then we have 3, that's the base radius, and then we have 6, that's the height of the cone. So you can see there are two similar triangles here. So we can use the geometry of the similar triangles, and we know that if there are two similar triangles, uh, their ratio of those corresponding sides have equal. They are the same. So that means in this case, what we're trying to do is we can write this one. So you can say using similar triangles, using similar triangles. So what we can do is we can write. So what we normally do, we write the one that we need to find on the top. So we can write this one as R divided by H is equals to, so R is corresponding to 3, small h is corresponding to 6. That means you get 1/2 here. So in other words, you can say R equal, you can say if you divide by H, so H over 2. So that's the value of R. And then what we can do now, we can use this value in the equation and try to simplify. So that means we can write this one as now, it's going to be 1/3 pi. R is equals to H divided by 2 squared times H. That means if you simplify all of them, you're going to see this is going to be pi over 12 h cube, pi over 12 h cube. So that is the equation, and you can see now we have only two variables. So we have one variable and another variable. So because those are the only information given, so we bring it to two variables. That's the next step. That's the second step. Now what we can do, we can take the derivative now. Okay, so the goal is to here, the goal is to you're going to find dh over dt when h equals 3 minutes. So the need to find dh over dt when when h equals 3 meters, because it said 3 meters deep. So deep means that's the how much the water is there. So it's like that's like a different wording that we normally use for the problem like that. So when you say deep, that's the number, how much water we have. So 3 feet deep water. Okay. So the next step is to find the relation. So what we do, we take the derivative now. So let's take the derivative now. So we can see. So when you say differentiating with respect to time, so we can write this one as dv over dt on this side equals pi over 12 is a constant. We're going to pull it out and then take the derivative uh, of h cube, and that's where we have to use the chain rule. So we can use the chain rule now. So we can write this one as pi over 12. So by the chain rule, we can write this one as d over dh h cube, d over dh h cube times dh over dt by the chain rule. Okay, so and if you finish the differentiation, you're going to get pi over 12, and if you take the derivative, it is 3h squared dh over dt. And if you simplify, you can see one of the 3 get cancelled, so you are gonna get this one as pi over 4 h squared dh over dt. Okay. So that means if you solve for dh over dt, that's what we are looking for, dh over dt. So you're going to get 4 over pi h squared dv over dt. So if dv over dt is a constant, this is again like, remember, like we had a similar problem in the blow balloon problem. So you can see that dh over dt is proportional to 1 over h squared. So this again inverse squared law problem. this for physics. Okay, now what we can do is we can plug in the values. We have given all the values, so if you plug in the values, you're going to say 4. So this is pi, and this is 3 squared times dv dt is given, which is 2. And if you put all the units now, so the 2 has cubic meters per minute, and the 3 has the meters, so it's a meter squared. So if you simplify, you can see squared get cancelled, so this gets cancelled with one of them, so you get only 1, and the number you're going to get is 8 over 9 pi. That's the exact value, meters per minute at that time. So we can write this one in words like this. So you can say the water level is rising at a rate of 8 over 9 pi, which is approximately 0.28 meters per minute. So units are important for problems like this. Okay, so let's look at the next problem. As the next problem, we have this very interesting problem. So these problems appear as either like a plane problems or car problems or things like that. So like two objects moving. So what it says that two small planes approach an airport, one flying due east. So one going to east at 120 miles per hour, and the other flying due north, going to the north direction, going to north at 150 miles per hour, assuming they fly at the same constant elevation, because otherwise the math would be really difficult if they're going in different levels. So the first part is asking how fast is distance between the planes changing when the eastbound plane is 150 miles from the airport and the northbound plane is 240 miles from the airport. So asking how fast the distance can change. So that means we can use, because since one is going east, one is going north, so there's a 90-degree situation here. So we can use the Pythagorean identity again for this problem like this. And the second part is asking if the eastbound plane has an option to change the speed. So the second one can change the speed. The eastbound one can change the speed. Is asking at what speed the plane distance at what speed of the plane the distance between the planes appear not changing for a moment. So you can see for a moment you can see that they are moving. So asking at what speed that can happen. So it's like a very interesting problem. So let's see how we can approach this problem. So again, of course, we can start with drawing a picture here. So let's do that. So we can draw the picture. So we can draw something like this. So first we have the radar tower, the airport, and then what happening is, so let's use this as a starting point. So one plane going to the east. So one plane going to the east. So that's one going to the east, and the other one is going to the north. So there's another one going to north. Okay, so let's mark the distance. So what we try to do is we're going to find this distance between the two. So that's like a main. So that's the situation. We assume that. So let's say this is O, the origin. And then so there are like there are several ways to do a problem like this one, and then it's very important how you pick the directions of each one. So what we can do is we can pick the distance from the airport. So we can say x, or it's like a function of time, so xt, which is the distance from to the eastbound plane, and the yt, which is the distance to the northbound plane. So this plane is going to the going to north at 150 miles per hour. These are small planes. Normally, like large planes go like with a much higher speed than this. So we can call this plane B. And the plane A, so you can see this is going 120 miles per uh, hour. When this distance is 180 miles and distance is 240 miles, so it's not into the scale. Okay, so like you can see, it's a round scale. Don't worry about that right now. Okay, so that's like a first one. So we draw like a nice figure and then try to put all the information in there. Now let's try to pick the variables. So we pick the variables also x and y. So I'm not going to write them just to save time. And then also let's try to put the information, what information that we have. So we know that, so uh, when x equal 180 miles, and then when y equal 240 miles, it's always a good idea to kind of understand what we have. We know that it's given that dx over dt, so that means the eastbound speed, you can see it's going away from, that means the distance is increasing, so that means a plus 120 miles per hour. And if you look at the plane B, it's going north. When it's going north, you can see yt is getting smaller and smaller and smaller. So that means it is a negative one. So dy over dt is negative because it's getting smaller. 150. This was a negative slope. If you look at there, so you can see it's a negative, so it's getting smaller. So it's negative slope. So 150 miles per hour. It's very important how you pick the variables. So it's getting smaller. Good. And then also you can do a similar problem using regular x and y directions, x coordinate, y coordinate, but in that case this dy over dt can be positive. So I'll be very careful how you pick the variables in this one. So actually I will do a different problem, the same problem in two different ways in another video, and you can find that also in the description, link in the description. So you can do this problem like multiple different ways, but you have to be very careful how you pick the those x and y variables here. Okay, so that's what we have. So in this way, so we take the distance. Since with the distance, so you can see x is increasing, that's positive, y is decreasing, so it's negative. So that's what happened. So we didn't worry about the directions. Otherwise, it looks like it's going to north. So if it's a regular variable, dy by dt is positive, but that's not what we are talking about. Why we take as the distance? So distance is decreasing, so it is negative. Okay, and then also we also need to find the distance between the two planes. So we can call it st. So from the Pythagorean identity, we can actually find this one. So you square 180, you square 240, and take the square root. So if you use a calculator, you can see that you can get 300 miles in this case, because they are all miles. Okay, so we have all the information that we need now. So now what we can do is we can write an equation and use the implicit differentiation to find it. So let's write the equation now. Using Pythagorean identity, because there's a 90 degree here, so using Pythagorean identity we can write this one. So using Pythagorean identity, we can write the equation. So we can say s squared, that's the hypotenuse, equal x squared plus y squared, because there's a 90 degree. So we can write it like that. Now what we can do, we can differentiate this one with respect to time using the chain rule. So differentiate it with respect to time using the chain rule. So you can write this one as ds over so s squared means 2s, so 2s ds over dt. It's very clear now. And then 2x dx over dt plus 2y dy over dt. So we did multiple examples, so we know this step right now very well. And you can see 2 get cancelled out. So we try to simplify all the way we can. And then you can see that we already know all of them. We already know s, we already know ds over dt, we know y, we know dy over dt, and we also know s. So only thing that we don't know is ds over dt. So we can solve for ds over dt So you have two ways to do this one, right? Actually, what you can do is you can actually plug in here if you want, or solve for ds over dt. So it's up to you. And if you solve for ds over dt, you get x dx over dt plus y dy over dt divided by s. So that's the dx over dt. So, and then what we can do is, so that's a formula. And then we know all of them. So we're gonna plug in. So let's plug in. So x, which is a 180 miles, and then dx over dt, which is 120 miles per hour, and the plus y, which is 240 miles. And be careful because we take the y as the distance, so it is positive if we write it like that. Yeah, as I told you, you can do this problem using the regular x and y coordinate. If you use a regular x and y coordinate, the 240 is negative. 240 is negative, but dy over dt is positive. So yeah, but this way we use the distance, so it is positive. So this is positive because it's the distance, and the distance is decreasing. That means it is negative. That's the negative sign coming from, because distance is decreasing. And miles per hour. Yeah, so we use miles. We use two different uh, units. So be careful with this. So both miles. Okay, and then uh, divided by 300 miles, and you can see all the miles get cancelled out. You can cancel out, so you get the final answer is miles per hour. And if you use a calculator, you should get negative 48 miles per hour. So that means the distance between the two planes decreases. The distance between the two planes decreases at a rate of 48 miles per hour. So we can write it like this. So I'm going to write it here. So the distance between the planes, so distance between the planes um, decreases at a rate of 48 miles. So since we say decreases, you do not have to say the negative, because you say decreases. That means negative. So you just say the number here. So that's how you write the final answer. So let's look at the next part of the problem. Part B says if the eastbound plane has an option to change the speed, at what speed of the plane the distance between the planes appears not changing. So so we know the equation that we get. So we can see clearly the distance does not change if the derivative is 0. So we can write it like that. So you can say the distance does not change if the derivative, that means ds over dt, equals 0. So that's the condition we can use. So we can use this condition, and we also know the formula from the previous part, which is x dx over dt plus y dy over dt. And what we do, we set this one equal to 0. So that's how we do. We just set this equal to 0. And so what we're trying to do is we use x value, y value, and dy over dt. What we're trying to do is we try to solve for dx over dt now. So that's what we're trying to do. So for what value? So so if you recall the situation, so that these numbers are still the same. This is 180, this is 240. So this one is only one. So we're going to see what is the new x prime, and we assume that this is ds over dt equal to 0 because the distance doesn't change. Okay, so it's like, it looks like not moving. This is called relative motion. So relatively they don't move each other. Okay, and then this one also we know this is 150. So only thing that we don't know is we try to find the x prime. This problem. So, okay, so let's plug in the values, and so we're gonna get so we have 180. X prime is the one we're trying to find, plus y is 240, and then dy over dt, which is negative 150, equals 0. And then if you solve for x prime, you're going to get 240 times 150 divided by 180. So if you simplify, so you can see that there are 360, there are 460s, um, and then also you can cancel 1 and you get 5. So that means you're going to get 200. So that means if the plane, small plane A, go with a speed of 200 for a moment, you're going to see the plane B will see that the distance doesn't change. Look like they don't move each other. Okay, so that's the speed that you're going to get. So if you write in word, so you can say if the eastbound plane flies with a speed of 200 miles per hour, the distance between planes appears not changing. Yeah. So yeah, it's like a nice interesting problem. Okay, so let's look at the next one. As the fifth problem, we have this very interesting problem. So what it says, an observer stands 200 meters from the launch side of a hot air balloon. The balloon rises vertically. That's like a big assumption here. It doesn't happen. It's like normally with the wind it's going to go, but we assume that rises vertically at a constant rate of 4 meters per second. So it's going to go up with the speed of 4 meters per second. How fast is the angle of elevation? So it's like an angle problem. Angle of elevation of the balloon increasing 30 seconds after the launch. So there are some distance calculation we had to do. It's like after 30 seconds. So because it says that it's go 4 meters per second. So that means after 30 seconds go 120 meters high. So we get some information. So let's draw a picture to explain the situation. So we have this. So there's a hot air balloon. So someone is observing on the ground. So you can see that there's a nice triangle here. We assume that this is 90°. That's like common observation. So the goal is to find how fast this angle is changing. This is what we normally call the angle of elevation. If the angle go down, we normally call this is the angle of depression. So let's put the information that we have. So we know that this is dh over dt. So how fast? So if you say this is h, so this is h, the height, and then it says that dh over dt, which is 4 meters per second. So that means if you wait for 30 seconds, this is h is simply 4 times that for 1 second, but there are 30. So that's how much meters you're going to get. So this is 120 meters height at that moment. So what we are looking, and then also we know that this is like 200 on the ground. This is 200, and then there are assumptions. We assume that the height of the observer is 0. I mean, those are like basic assumptions. Okay, and then what we are looking for is what is d theta over dt. So that's the one we are looking for. So let's try to relate those variables, like for example h and theta. So one thing that we can do is we can use one of those trigonometric identities. So one trigonometric identity is because what we have here is the we know the opposite is known for the angle, and also we know the adjacent. So the opposite and adjacent is related by it's a toa. So that means a tangent. So we got the tangent here. Uh, So using triangles, so you say using triangle, so we can write tan, so tan theta, which is opposite over adjacent. Opposite is h, the adjacent is 200. So if you cross multiply, you can write this one as 200 tan theta equal h. So that is the equation we are looking for. That relates the angle with the height, or no, you can see both of them are changing. So now what we can do is we can take the derivative. So we're going to differentiate with respect to time. So differentiating with respect to time variable, and you can write this one as so what we need to do is we need to take the derivative of tangent, and we know the derivative of tangent is secant squared. And if you are not familiar with the derivative for trigonometric functions, and you may find that in the link in the description about a derivative of trigonometric functions. Okay, so let's take the derivative. So it is 200. Derivative of tangent is secant squared. By the chain rule, we have d theta over dt term coming here equal dh over dt. It is one time dh over dt, so we don't write it. Okay, and then if we solve for, so what we need to do is we need to find d theta over dt. We can solve for that. So if you solve for that, you get d theta over dt equal dh over dt divided by 200 secant squared. But we don't know the secant, but we can write secant using tangent. So let's look at the trigonometry here. So what we can do is we can write the tangent first. We know the tangent theta, which is opposite over adjacent. Opposite is 120. Adjacent is 200. So you're gonna get, if you divide by 40, this is 3/5. Now we know this identity from trigonometry. Secant squared theta equal 1 plus tan squared theta. So we can plug in here now. So that means it's 1 plus 3/5. 1 plus 3/5 squared. So you get, okay, so that means we can do the same here. So it is, so we can write this one as dh over dt divided by 200, 1 plus tan squared theta. So if you do this calculation here, so you can see that this is 4 divided by 200 times 1 plus 3/5 squared. And if you use a calculator, so you're gonna get 0.015. In calculus, the answer is coming from radian per second, not from degrees. If you want to need how many degrees, you need to convert this into degrees, and we know that you need to multiply by 180 over pi. If you multiply this one by 180 over pi, you can get how many degrees per second. Okay, so that's the answer to the problem. So that's the how far the angle of elevation changes at that moment. Okay, so let's look at the next problem. This problem is very interesting if you are taking physics or engineering classes. So let's see what it says. So it says a particle moves on a circle of radius 13 millimeters in a clockwise direction. So particle moves on a circle on the clockwise direction. The projection of the particle on the x-axis, the projection on the x-axis moves to the left. All these information are very important. To the left with a speed of 7 centimeters per second. So it goes 7 centimeters per second when its x coordinate is negative 5 millimeters. When it's x coordinate, so we use the xy coordinate system for this problem. Find the speed and the direction. Find the speed and the direction of the projection on the y-axis. So I say what happened to the y-axis projection? So this is like a very interesting problem. So there's a particle moving on a circle on the clockwise direction, and so it's not like a uniform motion. It's like a it's maybe different speed at different times. So it says the x projection go at a 7 centimeters per second to the left when the x coordinate negative 5. So asking what is the y coordinate. So let's look at this situation um, as an animation. So you can see the situation as an animation. So you can see the particle moves on the circle on the clockwise direction, and then the x and y projection moves related to that. And then also this animation was done using Desmus, and you can find the complete program using here. And please use the link given here, and then you can access the complete animation, and you can also do something similar to that. And if you click those small arrows, and you can see the complete code there. So and also this link is given in the description. So so let's look at the mathematics behind now. So a particle moves on a circle, um, and so they have two projections, one on the x-axis. So we assume this x-axis. So we use a regular xy coordinate in this problem. And you remember, like in the moving plane problem, we use like a different coordinate, but here we use the same one. So there's a x and y projection, and then so this are gonna move in the clockwise direction. So that's a particle p, and then so what you can do is so let's pick some variables now. So we're gonna say so so let xy be the coordinate, be the coordinates uh, at time t. So that's the assumption, and then we can write all the information given. So what it says that dx over dt equal negative 7 centimeters per second. So negative means it's going to the um, left side. So it's going to the left side, so it is negative because x is decreasing on that direction. So it is dx over dt, which is negative 7 centimeters per second. And when x equal negative 5 millimeters. So these are in two different units, so be careful when you plug in there. Okay, and then also x is negative 5 millimeters, and also we are looking for dy over dt. That's what we are looking for, and then we don't know the y value, so let's also find the y value. So we can use a Pythagorean identity. So the goal is to find dy over dt. That's the goal. So let's use the Pythagorean identity first, and also we need to find the y. So using so you can say by Pythagorean identity, we can write x squared plus y squared equal, here the radius is 13, so 13 squared. So it is 5 squared plus y squared equal 169, and then we can solve for y. So y squared equal 169 minus 25, so which is 144. So that means y equal, you get a plus or minus 12. But you can see, let's use some information given. You can see it's going to the left direction, going to the left, and also x is dx or dt is negative. So that means it cannot be in the lower part, it has to be the upper part. Because if it's lower part, then dx or dt has to be positive. So that means y equal positive because of that. So y is positive. So positive 12. Okay, so we have that information. So that means this is 12 millimeters, the same unit. So that means you can see that only thing that we are looking for dy over dt. So we can use the we can differentiate the equation to find that information. So let's try to finish it now. So differentiating with respect to time by the chain rule. So we have, so I use a prime notation now. So it is, so we have what we have, x squared plus y squared equal 169. So if you get derivative, you get 2x x prime 2y y prime equals 0. And then 2 get cancelled, so you get x prime plus y prime equals 0. We are looking for y prime, so y prime is negative, and you can bring the xy term to the other side, so it's become negative. So what happened, x over y x prime. So that is the relation we are looking for, and then you can see that we have all three quantities on the left side. on the right side, so we can plug in this as negative. X is negative 5 millimeters, and then x prime is negative 7 centimeters per second, and the y is 12 millimeters, and you can see the millimeters get cancelled out, so you get the answer as it's a negative 35 over 12. So that's the exact value, which is centimeters per second. So it is negative. Negative means dy over dt, negative means going down. So it's going down at a rate. So we can say, we can write in word like this. So thus, the projection on the y-axis is moving to south, because negative means moving to south, with a speed of 35 or 12. So we said, because since it says south, you don't have to say negative. So we say 35 or 12 centimeters per second. Okay, so that's the answer to the problem. So let's look at the last problem, so seventh one. As the final problem of this discussion, we have this very interesting problem. So in this problem, actually, we have three variables now. So we have three variables. So we might need different formulas right now. So what it says, so there are three quantities, x, y, and z, change according to the equation. So that's equation. So what is xy squared minus x cubed yz equal 6 plus 3 square root z, and asking find dz over dt if dx over dt equal 2, dy over dt equal negative 3 when x equal 1, y equal negative 2, and z equal 4. So there are a few things here. So you can see that there are three variables. That's one thing you notice. There are three variables, and information is given for x and y. So that means you don't need to bring it to two variables, and you cannot, because there are three different variables. So what we do is we just take the derivative with respect to, so we do the implicit differentiation to find the derivative with respect to time. So let's do it now. So we start with the equation. So we have xy squared minus x3yz equals 6 plus 3 square root z. So one thing that we notice is there are three variables. So we had used the uh, three function derivative formula here. So if you are not familiar with that, and you can find the link in the description how to take the derivative when there are three functions. So what we can do, we're gonna take the derivative, so differentiate with respect to time, because given with time, both sides as before. So we have first term d over dt x y squared minus d over dt x3 y z, and then again d over dt. This side we have 6 plus 3 square root z. Okay, so let's take the derivative. So the first one, you can see that you take the derivative with, so it's a chain rule. So we use a chain rule for all of them. So you're gonna get, so if you take the derivative, the first one is a product rule. So it's a product rule for two terms, product rule for three terms. So if it's the product rule, so we take the derivative with respect to x first, so it's 1, and then we have a dx over dt times y. That's the first term. The second term means you take the derivative of the other term, so it is 2y dy over dt times x. So that's the first one. So this from that. Now we go to the next one. There's a negative, and you can see there are three terms. So when there are three terms, what we do, we take the derivative of the first one, multiply by this other two, and then take the derivative of the middle one, multiply by the first and the last, and then take the derivative of the last one, multiply by the first two. So, and again, and if you are not familiar with this formula, so you can use the link in the description to figure out what's going on here. Okay, so so you can write this one as, the first one is a x term, so that means 3x squared, and then we have dx over dt dx over dt, and then we have y and z. Next one, we take the derivative of the middle term, so it is we have dy over dt, and then multiply by the other two, x3 and z, and then take the derivative of the last term, which is dz over dt. So this is the product rule for three terms, and then multiply by the other two, which is x3y. So we're done with that side. So that's the derivative of the second term. So let's take the derivative of the last term. 6 is a constant, so it's 0. And then this is square root function. It's not difficult to take the derivative. So it is 3 times 1 half z to the negative 1 half, and then you have dz over dt. Okay, so now what we're going to do is, so that's the derivative of the last term. We're going to separate them into dx over dt terms, dy over dt terms, and dz over dt terms. So let's do that. So you're going to isolate them. So we have y squared minus 3x squared yc times dx over dt, 2yx minus x3z times dy over dt equal x cube y plus 3 halves 1 over square root z times dz over dt. Now what we can do is we're going to isolate this term. That's what we are looking for. So we can write this one as dz over dt equal divided by x3y plus 3 halves 1 over square root z. Okay, now what we can do, and you can see that we know all those terms, so we're going to plug in that to the equation now. So since dx over dt equal 2, dy over dt equal negative 3, when x equal 1, y equal negative 2, and z equal negative 4, so we're going to get a plus divided by, we have negative 2 plus 3 halves 1 half. So if you simplify, you're going to get 56 plus 24 divided by negative 5/4, which is equals to negative 80, the top become 80 over negative 5/4, which is going to be negative 64. So it's a negative number. That means negative slope, that means decreasing. So you can say C decreases with time. So we can write it like this. So you can say C decreases with time at xyz equals 1, negative 2, 4. So these are 7 problems. These are like 7 interesting problems that you need to know as a calculus student, and try to do them again and again. I mean, what you can do is just copy it down and then try to do it on your own and see whether you can get the same answer. And also you can, after you study all those 7 problems, and you can try the following problems as practice problems. So thank you so much for watching.